Today we're going to be looking at some weather data, and the purpose of this is to show you how to fit and visualize quadratic models in two variables. So the data are going to come from NOAA. NOAA is a government organization for atmospheric and oceanic research. So the data actually come from this website, the U.S. Climate Research Network. They have data from about 140 weather stations at the hourly level. So to get the data, you'd go to this URL, and then the data are organized by year. So if I click on 2019, there is a link for a weather station in Ithaca. So if I click on that, this is what the data look like. There's a bunch of columns and a bunch of information here. And the data come in every hour. So the definition for what the different columns are at this URL, and there's more information about each of the variables at this URL. And I went and downloaded data from 2013 to 2019. So this is the script. This script just reads in the data and then saves it to a CSV file that's convenient for us. So what we're going to be looking at are each day, 7 a.m. temperature and 3 p.m. temperature. And then we're also going to look at the day of the year. So we're going to see how the relationship between 7 a.m. temperature and 3 a.m. temperature change with day of year. Okay, so this is just the script to read in the data and save it in a format that's convenient for us. So this gets saved as if7a3p.csv. And this is the script we're actually going to look at, which analyzes the data. So for your working directory, you should be in the lecture code directory, btry60202020/lecture code. And if you're in that directory, you can read in the temperature data here. So if I do head temps, this is what the data look like. There's a column for 7 a.m. temperature. There's a column for 3 p.m. temperature, and there's a column for day of the year. So this is going to be a number between 121 and 269 or 70. So these are temperatures roughly between beginning of May and end of September. Okay, so here's our first plot of the data. Here I'm just putting the 7 a.m. temperature on the horizontal axis and putting the 3 p.m. temperature on the vertical axis. And then I've added a line for the 1-1 line, 1-to-1 line. Alright, so obviously there's a clear relationship between 7 a.m. temperature and 3 p.m. temperature. Looks to be increasing and roughly linear. You can also do the same thing for a day of the year. This is where things kind of get more interesting. So clearly it's cooler in May and then warmer in the middle of the summer and then begins to cool off again. Thing that's really interesting is when you start looking at this as a three-dimensional or two-dimensional plot with 7 a.m. temperature on the horizontal and day of the year on the vertical, and then the color tells you the 3 p.m. temperature. So the way I'm making this plot is, first thing I do is this, the function I'm using to plot will complain if there's missing values in the data. So first thing is I check for missing values, and then I plug in into this quilt.plot function, which is in the fields package. This is a way for conveniently plotting three variables together. So first argument is the horizontal axis, second argument is the vertical axis, the day of year, and then the third argument is the response, so the the variable you want to plot in color. And then I give some X labels and Y labels. So this is what you get. And you can see, somewhat already kind of interesting is that in the early part of the year, so this is like in May, a cold 7 a.m. temperature indicates a cold 3 p.m. temperature. So you could see that by seeing that the colors are blue here, whereas a cold 7 a.m. temperature in September indicates a warmer 3 p.m. temperature, as opposed to what you would get in May. Okay, so something maybe a little bit interesting is that right now you can see it's March 22nd, and it's kind of cold today, but it can still be cold in May here in Ithaca. So what you're seeing here is there was one observation between 2013 and 2019 where the 7 a.m. temperature was below freezing in May. And it can be, so this is in Celsius, so this is freezing. And it can be pretty cold still in May in Ithaca. So the idea here is we're going to try to fit some models to these data where 3 p.m. temperature is the response and the predictor covariates are 7 a.m. temperature and day of the year. And you can see that there's kind of an interesting relationship between these three variables. So first model will fit, we're going to fit a bunch of models, 6 models here. The first model we'll fit is a model with just 7 a.m. temperature as a covariate. And so this is a linear model, linear in 7 a.m. temperature, and clearly there's a strong relationship. An increase in 7 a.m. temperature by 1 degree gives an increase in 3 p.m. temperature by 0.6 degrees. Alright, so that's not too surprising. There also is a linear effect of day of year. This is kind of not quite the model you would want to fit. The reason is because we're looking at a period of the year where temperatures kind of increase at the beginning and then level off and then start to decrease at the end. So really we'd want to fit a quadratic model. So let me add that here. So I think what we'll find is this quadratic, I'll call this M2A. This quadratic model is a much better fit. So the way you add or one way to add a quadratic in R is to do I is a function in R, and put the DOY squared. The reason you can't just leave this as DOY squared is because, well, let's see, it'll give an error. Oh, didn't give an error, but it doesn't do what you want it to do. And you can see the model that it fit just has DOY, day of year, as a linear covariate. So the way you add it as a quadratic is to enclose it in this I thing. And this does give you what you want. So let's compare these two models. The quadratic term is significant and it's negative, which kind of makes sense. Well, definitely makes sense because a negative quadratic means it's concave down, which is exactly what you saw in this plot here. So there's a concave down shape. This quadratic model is a better fit than the linear model. So the linear model had a residual standard of error of 4.841 and it decreases to 4.3 in the quadratic model. Okay, so we think there's both of these variables should go in the model somehow. So here's the additive model with 7 a.m. and day of year in the model. So these are a linear additive model. So this is somewhat interesting. What this is saying is that even after you control for 7 a.m. temperature, day of the year still has a linear effect on the response. and it's positive. So there is some information in this day of year variable as it relates to 3 p.m. temperature that's not explained by the 7 a.m. temperature. Okay, so if we keep going, we might want to fit an interaction. The interaction significant. This also kind of makes sense if you think back to the plot. So let's look at the plot. Remember what the interaction model says is that the effect of 7 a.m. temperature, which is the slope of 7 a.m. temperature, changes with the other variable, which is day of year. So the effect of 7 a.m. temperature is linear, but the linear effect changes with day of year. And that's exactly what you see here. So for this day of year, there is an effect of 7 a.m. temperature. The 3 p.m. temperature increases with 7 a.m. temperature. So that's what you see as you move along this axis. And it's a pretty strong effect, meaning that cold 7 a.m. temperatures correspond to cold 3 p.m. and hot 7 a.m. temperatures correspond to hot 3 p.m. temperatures. But the effect is actually weaker at in later days of the year. So still, the effect of increasing 7 a.m. temperature is to increase 3 p.m. temperature, but the effect is not quite as strong. So if you were to kind of visualize this in your head, there's a steeper slope here as you increase 7 a.m. temperature, and a less steep slope here as you increase 7 a.m. temperature. So it's no surprise that there's a significant interaction term, and that the interaction coefficient is negative. So what that means is that as you increase day of year, the slope with respect to 7 a.m. temperature decreases, which is exactly what you see. You have a big slope here and a smaller slope here. All right, so like we said above, the day of year effect should probably be quadratic. So this is a model that has quadratic effects in 7 a.m. temperature and day of year. And this is still technically an additive model. So our definition of additive model is that the effect of one variable doesn't depend on the value of the other. So this is, we can call this an additive quadratic model. And you can see as we're increasing the number of terms in the model, the residual standard error is going down. So for the additive model, it's 3.96. For the interaction model, it's 3.92. It's a little bit better actually for the additive quadratic model. And then the most complicated model we'll fit is the full quadratic model. So this has interaction effects, so additive and interaction effects between 7 a.m. temperature and day of year. And then we also add the quadratic terms. If we do that, now we get 6 coefficients here. Intercept, 7 a.m. temperature, day of year, quadratic in 7, quadratic in day of year, and this interaction term. So it can be interesting to do some testing here. So we have 6 models, and some of the models are special cases of other models. So when that is true, you can do an F-test. And the way I like to do the F-test so that I don't confuse myself is to put 2 variables in the ANOVA, two models in the ANOVA function, and then I know exactly what R is doing. It's doing an F-test to compare these 2 models. Okay, so this first one is model M1 and M3. When you do ANOVA, it'll print out the 2 models. So what we're testing for here is, does day of year have a linear effect on 3 p.m. temperature after controlling for linear effect of 7 a.m. temperature? And we get a tiny p-value, 3.97 times 10 to the minus 11. And this should be the same p-value on the day of year coefficient in this model. So yes, this is exactly the same p-value here. So here we're just testing for one additional covariate, and therefore you can do a t-test for that as well. All right, we can do the same thing for adding temperature to a day of year model. That's not too surprising. Here we can test for an interaction. So M3 is the additive linear model. M4 is the interaction model. So the interaction is significant, and this is something that we saw when we just looked at the summary for the interaction model. So this p-value is the same as this one because you get the additive model by removing that term from the interaction model. Let's see, you can compare M4 and M6. So M4 is the interaction model, M6 is the full quadratic. So the full quadratic adds these two terms. Now here you can't do this comparison with a t-test because you're adding two additional terms here, and that's significant. So we have evidence that the full quadratic model is better than the interaction model, and you can also compare the additive quadratic to the full quadratic. And again, we have information that we have evidence that the full quadratic model is a better fit than the additive quadratic. Okay, so next thing I want to do is to visualize these models. The way we're going to do that is to create a grid of points at a bunch of different 7 a.m. temperatures and a bunch of different days of the year, and then we're going to make like a heat map of the fitted 3 p.m. temperature, estimated expected 3 p.m. temperature as a function of these two variables. So this block of code creates these grids. So we're going to look at 7 a.m. temperatures on a grid between 0 and 25 degrees Celsius. So just let me print this out so you see what that looks like. So we're looking at a range of 7 a.m. temperatures. We're looking at a range of days between day 120 of the year and day 270 of the year. And then we're going to look at all possible combinations of these two variables. The way you calculate that in R, there's a function called expand.grid. So you just put in the two values, and let me do plot these to show you what they look like. So what this does is it takes every variable in this vector and pairs it with each variable in this vector. So this will go from 0 to 25, and it will pair it with the first variable here, and then it'll move on, do this again, 0 up to 25, I've cut it off here, and pair it with the next variable here. So it does all possible combinations. And then we're going to put these interaction and quadratic terms here. So this is a data frame with two columns, temperature and day of the year. I'm going to create a third column for the product. So this will be for incorporating our interaction terms. A fourth column for the quadratic in 7 a.m. temperature, and a fifth column for the quadratic in day of year. And then I'm also going to save a vector of 1s because we have an intercept in all these models. All right, next thing to do is actually make the plots. So the way I'm going to do this to make this as easy as possible is for each model, I'm going to create a data frame that has the variables that are in that model. So for example, for M1, this is the model that just had intercept in 7 a.m. temperature. So I'm going to create a data frame that has this 1 vec for the intercept, and then I'm going to grab the first column from temp day grid, and the first column for temp day grid holds the temperatures. The reason for this is I can calculate the fitted values quickly by just taking the this matrix and multiplying it by the model coefficients. So we haven't covered matrix multiplication, but this is just a convenient way for me to write the R code to calculate the fitted values. Okay, so that calculates all the fitted values. And then I'm going to use, to make these 2D plots, I'm going to use a function called image.plot in the fields function. This is a very convenient function that allows you to plot a matrix of data. So what I'm going to end up doing is I'm going to take the 3 p.m. temperatures, put them in a matrix. So it's going to be a matrix that has n-grid rows, one for each 7 a.m. temperature, and n-grid columns, one for each of the day of the year, at least the grid of days of year that we're using here. And then this plots it. So the first argument is the grid of temperatures, second argument is the grid for day of the year, which goes on the vertical axis. This is the value that's going to be given a color in the image plot, and then I'm telling it additionally the limits of the colors that we're going to use. So let me just plot this. Okay, so this is what the plot should look like if you have a model that just has a linear effect of temperature. So as you increase along temperature, 7 a.m. temperature, the 3 p.m. temperature increases. So that's exactly what we expect. But this model has no effect of day of year in it. And so the way you see that in the plot is that the expected 3 p.m. temperature for a given 7 a.m. temperature does not vary with day of year. So if you look along take any 7 a.m. temperature and look along the transect for day of the year, this is constant. Alright, so you can do the same thing for the model that just had day of year. Here we're grabbing the second column of here because the second column is day of year. Let me plot that. Here you get the opposite effect, where for a given day of the year there's no effect of 7 a.m. temperature. That's because we didn't put 7 a.m. temperature in this model, but there is a gradient with respect to day of the year in this model. Alright, so these are what the linear models in each variable look like. Here's the additive model. So the additive model was M3. Here now I have to grab both the 7 a.m. temperature and the day of year variables from this grid. And this makes the plot. Okay, so now you can see that both variables have an effect here. So for a given day of the year, 3 p.m. temperature increases with 7 a.m. temperature. For a given 7 a.m. temperature, the 3 p.m. temperature increases with day of the year. So the defining aspect of this additive model is that for a given 7 a.m. temperature, the effective day of year is linear. For a given day of year, the effect of 7 a.m. temperature is linear, and the slope of both of these linear effects does not change with the other variable. So the slope here is the same as the slope here in the additive model. Likewise, the slope with respect to day of year at this 7 a.m. temperature is the same here as it is here. Now the actual expected value is different for these different choices, but the slopes are the same no matter which day of year you pick or 7 a.m. temperature you pick. Okay. Now for the interaction model, that's not true. So the interaction model allows the slopes to vary with the other variable. And so this is the first one that's kind of interesting here. So remember when we looked at the data, let's see if we can go all the way back. we observed that the effect of 7 a.m. temperature was stronger for May than it was for September. And if we go look at this interaction model, that's exactly what the model is telling us. So if you think of, kind of try to visualize how steep the slope would be with respect to 7 a.m. temperature for this day of year, so this is like in May, it starts very low and then it gets very high, so that means a steep slope. For September, it starts at a moderate value and doesn't get quite as high, so this is a shallower slope. So the slope with respect to 7 a.m. temperature is different here than it is here. And so that's kind of the defining characteristic of the interaction model. The same can be said of the effect with respect to day of year. And maybe this is actually a little bit easier to see. So if we look at the effect of day of year when 7 a.m. temperature is 21, or 20 or 21, it's basically nothing. So maybe here, maybe 19 is the 0 point. So the slope along this axis at temperature equals 19 degrees is essentially 0. Whereas the slope with respect to the day-year axis when the temperature is 5 degrees is positive. So it increases here and it's 0 here. Okay, quadratic model is this one. So the quadratic model means there's like a hump or a bell curve or something like that. So the defining factor of the additive quadratic is that if you remember back to when you learned about quadratics or ellipses, is that the ellipses are aligned, the major axes of the ellipses are aligned with the axes. So if you have an additive quadratic model, this major axis is going to be aligned with the x-axis. Whereas in the full quadratic model, it allows any type of ellipse. So here the major axis is like along here, and it's not aligned with either of the two axes. So this is what the full quadratic model gives you over the additive quadratic model. Additive quadratic model forces the major axes of the expected temperatures to be aligned with the two axes, whereas the full quadratic model allows the major axis to go at a diagonal. And this was a better fit to the data than the additive quadratic model.